All right. So, okay. Can folks see this?
Yeah, I think the conference room can see the screen as well.
Sweet. All right. Cool. So, today I want to talk a little bit about, different take on pre-training than I usually have. So, specifically, I want to talk a little bit on post-training than I usually have. So, I want to specifically talk about what simulation can do for robotic post-training. And so, to start off, I want to, acknowledge all my students first in the Weird Lab. They're the ones who do all the work, and so I want to start off by acknowledging them. Okay, so uh, maybe before we get into post-training for robotics, let's think about where post-training has been super successful in machine learning, right? So the domain that's the most top of mind for most of us is is that of language modeling, right? So post-training has been particularly effective in language modeling, and so when I think of post-training, I'm thinking of things like RLHF or RLVR, and so you have a large pre-trained language model that's trained on a large corpus of data. It's pretty capable. And you then want to fine tune it on a particular set of things with RLHF or RLVR to be particularly capable, remove toxicity, give it reasoning capabilities, and so on. Right? And so the pre-training puts everything in a reasonable regime, and then the post-training kind of optimizes for particular capabilities. And so that's kind of the model of post-training with reinforcement learning that's been really successful in language models, right? And so let's take a closer look at what's made this work, right? So maybe the first element of this is data. And so we have a huge corpus of data. That's what's used to pre-train your models. That's what's used in reinforcement learning too. And so data is certainly an important element. Second is your model or your algorithm. You want a large model that can accept all of this data and an algorithm that can actually be stable and trained to improve this, right? And so a lot of focus in machine learning research goes towards the model or the algorithm. But the third thing here is the environment, right? So if you have a reinforcement learning system, all reinforcement learning systems have an agent and an environment. And a lot of the times the environment is a bit overlooked, but it's super important in order to ensure good performance, right? So for things like RLVR, the environment is things that gives you the verifiable reward. And so my claim is that if you look at where post-training has been successful, in this case, we should consider the data, model, and the environment, but let's focus in on the environment for this talk. So what is the environment in LLM post-training, right? So the environment is kind of interestingly weird for LLMs, right? So the environment is just concatenation, right? So if you think of an LLM generating things, you just have a previous prompt being your current state, you generate an action, which is a completion, and then you just concatenate that completion and you generate the next thing, right? And so your dynamics is almost trivially simple. And so, unlike robotics, where you have a separation between action and state and so on, weirdly in LLMs, your model is kind of similar to your policy. And so, the dynamics are somewhat simple. But the important thing for post training is what this kind of synthetic environment enables for RL, right? And so, if you have this simple dynamic synthetic environment, it enables some important things, right? So, the first thing is that because all the samples are in imagination, samples are cheap and safe, and they're faster than real time, right? You can keep generating them as long as you can make your GPUs keep running, you'll keep generating interesting things. Second, you can reset the model wherever you want, right? So let's say you had a completion, you made a mistake, you can reset that model to that partial completion and then try again, right? So you get resets for free. And lastly, you have something that is like trivially parallelizable. So let's say you had something where you had these prompts and these completions. You could start at a particular, partial completion, and then in parallel sample a bunch of different things and score them. And that's kind of what powers algorithms like GRPO and so on. And so these three things, while they seem simple, really help with reducing the variance of reinforcement learning or policy search, and they make post-training a lot easier, right? And so I kind of think of LLM post-training as kind of doing RL in a model or a simulator. But, we're at RSS. We want to do RL on robots, right? We want to get post-training to work on robots. And so the unfortunate fact is for robots, these privileges don't exist, right? So for a robot, your samples are slow. And so if you have to take, let's say, 10 million PPO samples, it's going to take you at least 10 to 15 days, if not more. right? And then the world is not trivially resettable. You can't teleport to wherever you want. And so a lot of these benefits, the things like GRPO that we talked about doing earlier, are a lot harder to do on robots trivially, right? So in some ways, doing reinforcement learning on robots is hard in different ways than it is for LLMs. And I think this is a pretty exciting research area, and I've been thinking about it for several years. But it kind of spawns a bunch of interesting research questions, right? So things around offline to online RL, things around what the rewards look like, things around reset-free learning, right? And so in all of these cases, you have open research questions because you can't assume infinite samples, you can't assume safe data collection, you can't assume infinite resets, right? And hopefully Jianlan, who's going to be talking later today, will have some interesting insights on this matter. But today I'm instead going to try and focus on a different aspect of post training. Right? So I'm going to specifically try and focus on, well, we think LLM RL works well. Can we make robotic RL look more like LLM RL, right? So can we cheat in certain ways to make robotic RL and robotic improvement in the real world look a lot more like what RL for LLMs does, right? And the leverage we're going to use here is to use physics simulation. Right? So when I say we want to use physics simulation, we're going to try and say, have a real world policy. We're going to put it in a simulator and try to improve it with RL in that simulator. Right? So when I talk about a simulator here, I'm talking about something like Mujoko, ISIC any GPU parallelized physics simulator. Right? And so the point of doing this kind of bridge is that if you do it properly, you get a lot of the benefits of what LLM-RL, uses to do so well. Right? So, for instance, your samples are cheap, safe, and efficient. You can reset to wherever you want. Your model is trivially parallelizable. And so, all of the things that made LLM-RL tick, you can also get to tick on robots. You just have to do RL in simulation, right? And so, the hope here is that we can leverage some of these benefits in order to get improvement for robots in simulation, and this will reflect in improvement in the real world. And so specifically, I'm going to be talking about a recipe for real to sim to real improvements, right? So we're going to start with real world policies, and that's going to be things like our generalist foundation models, our VLAs, and so on. We're then going to go into simulation and try to improve these policies in simulation. And then finally, we're going to come back to the real world and show improved performance in the real world, right? So unlike LLMs, where the training and the deployment environments are exactly the same, here we're going to have the real world and we're going to have simulation. So the first phase is going to be what we'd call real to sim policy improvement, right? You take your real policies, improve them in simulation. And the second part is what you call sim to real policy improvement. So you have your simulated policies, you put them in the real world, and then get them to improve. Right? The key challenge that kind of plagues both of these things, which is not a challenge for LLMs, is that there's a mismatch between the environment where you perform your improvement and the environment where you perform your deployment. Right? So you're performing improvement here in simulation, but you're deploying in the real world. And at the end of the day, you have to operate under the conditions of the real world, right? And so this mismatch is going to manifest differently for real to sim improvement and sim to real improvement. But this is kind of the fundamental mismatch that we're going to try and study. Right, so the focus of this talk is going to be how do we develop post-training recipes for robotic foundation models that account for domain mismatch either from real to sim or from sim to real. All right, so and we're going to ensure that since the workshop on post-training foundation models, we want to make sure it's applicable to large pre-trained models, and we want to make sure that we're doing this in the real world, like we're measuring performance in the real world. Okay, so let's think about the first part. How do we perform policy improvement from real to sim? Shiro, how are we doing on time? Question for you. How are we doing on time? 20
Hi.
minutes? 20 minutes? How long do we have left?
We still our total time is 30 minutes.
How much time do we
Yeah.
have left? Tw
Yeah.
20 minutes? Okay.
We still have 20 minutes.
Okay, great.
Yeah.
Okay, so the first question we're going to ask is you have policies in the real world. You want to go and improve them in simulation, but you want to account for the domain mismatch while doing so, right? So how do we do that? All right, so we're going to start from the most obvious thing, right? So we're going to say, hey, we have some real world policies. We're going to train them with imitation learning or something. They'll work sometimes, they won't work sometimes, they'll make mistakes, right? Then we're going to stick them into a simulator, and we're going to use our favorite RL algorithm. Let's say we're going to use PPO, right? So we're going to use large scale PPO to do simulated policy improvement. And this is kind of like your RLVR step or something where you, let's say, have a sparse reward that rewards you for success. And you're going to use this for policy improvement. And then finally, when you're done, let's say you transfer it back to the real world, you can do distillation or something like that to take your improved simulated policy and bring that back to the real world. Okay, so there's a standard recipe for real to sim to real policy learning. Let's apply it, right? And so what you'll see happens when you do this kind of thing is you'll see that it'll solve the task, right? It'll maximize the reward, but often what will happen is it'll do it in a way that totally exploits the simulator, right? So because there's a mismatch between sim and real, and there's things that are unrealistic in the real world but can happen in your simulator, you'll often find that unconstrained RL basically exploits the simulator. And when you try and apply that to the real world, you see that things go terribly wrong. So on the top, you'll see here that we broke the finger of the robot or you hit into the table, like behaviors that, are okay in simulation but are just not okay to deploy in the real world. And so this kind of stems from this mismatch of dynamics between the real world and simulation. Okay, but now there's an obvious solution here. The first one is reward shaping, right? So you can say, oh, don't hit the table and go this way and apply this much energy and so on. But if you have to do this for every single problem, this quickly becomes pretty tiring. Okay, so but the LLM community, again, taking notes from them, has thought about this before too, right? And like a huge literature on RL even before that has thought about doing KL constrained optimization. So saying, let's try to optimize rewards in simulation, but let's make sure that the policy is constrained to not go too far away from the initial base policy it started optimizing from. And so the scale constraint optimization is a great way to like ensure that you have some conservatism, right? So the first term is trying to say let's maximize the reward in sim. The second term is trying to say let's stay close to the base policy to avoid exploiting things. And so, in some sense, as you change this constraint weight, right? This constraint weight can go from weak to strong, and when it's weak, it often you'll see that it tries to exploit the simulator, and when it's strong, it becomes hard to improve, right? So if you're over constrained, you stay pretty close to the base policy, but if you're under constrained, then you get back into the scenario where you're exploiting. So for every problem in every instance, you have to then go and like tune these parameters to get it to work, and this quickly becomes hard to scale, right? Okay, so distributional constraints like the one shown here are reasonable, but they're often hard to scale, especially when you're trying to balance between conservatism and optimism, right? Optimism to do improvement and conservatism to avoid this exploitation behavior. So the question we're going to ask here is how do we actually get a solution that balances conservatism with improvement without having to tune these parameters per domain and per instance? And so the insight we have here is that rather than having a distributional constraint, let's consider something like a support constraint instead. And so what I mean by a support constraint, right? So let's say we consider this distributional constraint as we had before. We're trying to, let's say, maximize reward. And you want the learn policy to be close to the base policy, right? And so what happens is as you change the weight, you'll see that there's exploitation. If the weight is too high, it's too conservative. Now, instead of a distributional constraint, we'll propose a support constraint. And what a support constraint says is that don't worry about getting the distributions to be the same, right? But instead, just say that wherever the base policy has support, the learn policy can have support, right? So you only want the likelihood of the learn policy to be non-zero, where the base policy has non-zero likelihood, right? So in these figures, this blue band in the middle is where the base policy has likelihood. You'd never want to optimize outside that. Right? So the nice part here is that you don't have to worry about like getting the distributions exactly the same. You can sharpen anywhere within the support, but it's often quite hard to enforce this constraint. So a support constraint allows your policy to change more, but it's hard to enforce. And so you have to do all of these fancy kernel tricks and so on to enforce them, right? But what we're going to try and do is enforce a support constraint, and that's going to make our life easier, right? So when we have flow and diffusion policies, the nice thing is that they offer us a knob to easily enforce these support constraints, right? So all you're going to do is just perform steering unconstrained in the noise space of these flow or diffusion policies. So a few years ago, we had this paper called Diffusion Steering, and building on that paper, essentially what it says is that if you have a mapping from noise space to action space, you can perform reinforcement learning in that initial noise space, right? And what we see here is that when you perform reinforcement learning in that initial noise space, it allows you to do support constrained reinforcement learning. So you never go and do exploitative behaviors because you're just searching in the space of initial noise, right? And so then your optimization starts to look a lot more like the thing on the right, where you only stay within the support of things that you know, right? But you're able to perform significantly better than you did at the start. So the main point here is that we're going to take a policy from real to sim, and then we're going to do reinforcement learning, but only in the initial noise space of that policy. And doing so prevents all of this exploitation behavior while allowing for improvement, and there's no tuning of any weights and stuff like that, right? So these kinds of methods have typically been used to get really efficient real-world RL, but here we're arguing that it also helps with constraining behavior when doing real-to-sim optimization. And so the overall algorithm looks like this. You start with behavior in the real world, you take it to simulation. It might not work that well, right? Then you say, I'm going to perform reinforcement learning with large scale RL in simulation to steer it to performing the task particularly well, right? So you improve success rate and throughput and so on in simulation through large scale RL. And finally, what you transfer to the real world, you don't change anything about the base policy. You just transfer the steering policy from sim to real. So you just learn how to steer in simulation and transfer it from sim to real. That's it, right? And what that results in is a policy that's way more successful, way faster, way more robust, and so on, right? And the benefits here is that you can apply it to arbitrary policies. It's safe, fast, and cheap. You get all the benefits of simulation. You get improvements in success rate and throughput, and you don't have to do a lot of reward engineering, right? So it kind of gives you those nice benefits that RL and simulation or in a model gives you. Okay, so let's quickly look at some results. And you can see here that, these are base policies on the top. And when you improve them with this kind of a simulation-driven steering approach, you get significantly better success rates, right? So you get, over 2.4x improvement and significantly faster performance. And that's coming just by steering. You're not touching the base policy. You're just learning how to steer it. It's also applicable to things that are, more interesting. So things that are higher dexterity. So opening this Clorox bottle or, picking up a book. And it's robust enough to like retry and keep repeating things so you can run things continually, right? So the cool thing about an approach like this is because all you're learning to do is steering and simulation, you can bring up new tasks super quickly. You don't have to do a lot of training for every new task. Okay. I will skip this for the sake of time, but the insights kind of in this first section are, policy improvement in sim can be exploitative. You need to account for this dynamics gap. Flow steering can give us a simple way to enforce support constraints, and you want to put RL in the setting where it does particularly well, right? And so you want to put it in the setting where you have abundant samples, lots of resets, cheap data collection, and then you can just learn to steer and do significantly better. Okay, so that's section one. I'll pause for if there's any questions,
Yeah, so if anybody have some questions for Abhishek?
or I can stop at the
Yeah.
end. If that's easy.
Yeah, so I think I have a small question.
Sure.
In DSL, we improve and optimize the model performance and by modifying the noise distribution and
Yep.
sampling rules. Would this approach become ineffective if the base model itself lacks sufficient
hmm
inherent capabilities, such as it can perform task one, but if we want to transfer it to task B, and it
Yeah.
cannot performs task B well. So do you think that DSR
Yeah.
will perform well on this scene?
That's a great question. So, so this is actually the slide that I skipped. What you need is that you need the base policy to have good coverage. You don't need it to be perfectly good, right? So
Yeah.
if it's successful 0 times on task two, then you're in trouble. But if it's successful sometimes on task two, then you can refine it, right? So I think what's really important is that on a new task, you want it to have enough coverage, but not necessarily be perfectly good on it. And so you find that on the plot on here on the right, you see that if you add in broad coverage data, you get a lot of improvement. Whereas if you have
Yeah.
narrow coverage data, you don't really get that much improvement.
Yeah.
Cool. All right. Let's keep going. So the first part said, okay, if I had policies in the real world, I can go and improve their behavior in simulation. through this kind of latent steering, right? And now I've done this latent steering, but I bring it back to the real world. How do I make sure that I'm able to either be successful in the real world or keep getting better quickly? Right? So we said that I showed you a bunch of videos of, the successful sim to real transfer, but it doesn't work everywhere, right? So if you look at a couple of different behaviors where you have success in simulation, right? So you have success in simulation with dynamics, which are non-trivial, right? So you see that when you transfer them to the real world, you often have some sort of drift that comes, right? So on the left-hand side, there's like different dynamics of the ball. On the right-hand side, there's different dynamics of contact. And in both of these cases, you see that this dynamics mismatch between sim and real is going to lead to some performance drop, right? And so I'm gonna channel my PhD advisor, Sergey, and he always said that there's no substitute for real world experience, and I agree. The question is, can we still use the simulated stuff that we had from before to make real world experience way cheaper and get away with a lot less real world experience? Right? So inherently simulation is wrong, right? I think we have to accept that simulation is a model of the world and it's wrong. And I can spend more time trying to make sim and real closer to each other, and that'll certainly help, right? But at some point, there's a question of should I be spending more time trying to make sim more accurate in every different scenario, or should I be spending more time trying to use that wrong simulator in order to improve behavior in the real world, right? So the key point to take away here is that wrong doesn't mean useless, right? So just because the simulator is wrong, hopefully it can help. Hopefully it doesn't mean that it can't help with improvement, right? So the question I'm going to ask in the second part of the talk is, what can we actually take from a wrong simulation to improve real-world reinforcement learning, right? So the idea here is that we said real-world RL is going to be hard, but we said it's hard when you're learning from scratch. So when you're learning from an initialization in sim, can we make real-world RL a lot easier, right? So the broader question to ask is, what can we take from simulation beyond just a policy that can make real-world RL fast? Right? And so we want to go from things that are a little unsuccessful, like the thing on the left, to things that are a lot more successful at solving things on the right, just through small amounts of 10 to 15 minutes of real-world experience. Right? Okay, so the high level question that we need to think about is what can simulation actually capture? What is it good at capturing, right? So in general, I think of a policy as kind of doing two things. One is it's kind of doing global planning. It's figuring out that if I have to do furniture assembly, I have to reach towards the object, I have to pick it up, I have to approach it in a certain angle, and so on, right? And then it's actually figuring out what the low-level actions are to execute those things and how do you apply the forces on the robot at every step. Right? And so you have this process of global planning, right? Figuring out the strategy to solve your problem and which states do you visit. And then you have local acting, right? Figuring out what actions go between those states. And the argument we're going to make here is that the global planning, the rough structure of how to solve tasks, transfers between sim and real, and sim kind of gives you a good sense of how to do that. Whereas local acting, which is trying to get the like tiny adjustments to fix low-level control, is not well captured by sim, especially when dynamics are really important, right? So we're going to say the global planning is captured by a value function, and the local acting is captured by something that looks like a policy or a model, right? And so the question we're going to ask here is how do we transfer the global planning from simulation to the real world and use that to make the search problem a lot easier for reality, right? So in general, RL is hard because you're solving a long horizon exploration problem, you're solving a long horizon search problem. But what we're arguing here is that if we can transfer the global planning from sim to real, then all you're doing in the real world is you're solving a short horizon search problem, right? So you're killing the horizon of your problem. And so if you have a short horizon problem, that's super efficient, right? And so what we're going to try and do in this section is we're going to say, hey, we've done simulation. It captures the global structure. We'll transfer things from simulation to make the search problem in reality a short horizon fast search problem. Okay, so the question we're going to ask is how do we reduce the effective horizon for RL in the real world based on simulation pre-training? And so there's a bunch of different ways to do it, but we're specifically going to focus on a model-based RL way of doing it, right? So what we're going to say is that based on work done by my students Tyler and Jake, we're going to try and learn a latent dynamics model from simulation. So a latent dynamics model just goes from observation to a latent, latent to a future latent, and a future latent to future rewards and future values. right? So just like a standard latent dynamics model, Dreamer, or like TDMPC or things like that, right? And we're going to just distill this from simulation. And then the argument here is that the encoder, the rewards, and the values can be frozen from simulation because they capture the global planning, the long horizon structure. And the latent dynamics is the only thing you need to adapt to the real world data because it's just short horizon local dynamics. Right? And so the argument being you can freeze a large part of the model and just adjust the latent dynamics. Right? So the once you adjust the latent dynamics, you can then use this for short horizon planning to improve your performance. So how do you train these models from simulation? Well, it's just supervised learning, right? So you've done some RL process, it's given you a policy, it's given you a value function from some PPO thing, right? And then all you're going to do is learn the rewards, the values, the latent dynamics, the encoders with supervised learning. Right? So just a simple supervised learning procedure, right? But the important thing is when you do this kind of process, you need to make sure that you're doing it on high coverage data. So if you're doing model-based planning, right, you need to make sure that you have high coverage of not just optimal behavior, but also counterfactuals, right? So you want to include things like action perturbations, so things where you have noise added to the performance, or you want to include like past checkpoints, right? But in general, what you can do is you can take a bunch of the data that we trained in the first section, use that to distill it into a latent dynamics model. But the cool thing is when you deploy it in the real world, I don't need to do any fancy RL stuff. I just need to fine tune a short horizon latent dynamics model, right? So I'm going to start from a policy. It's going to propose an initial action chunk. And then I'm going to have to do planning around that initial action chunk using my latent dynamics model. But as I collect more and more data in the real world, I just adjust the latent dynamics model and keep everything else frozen. Right? So then in the real world, I'm just adjusting by doing supervised learning, and I'm solving a short horizon planning problem. There's no long horizon off policy RL. It's a super simple adaptation procedure. You're just adjusting latent dynamics with supervised learning. That's it, right? And so the point here is that we've like converted this adaptation procedure into a short horizon planning problem and a supervised fine tuning problem. And in doing so, you can get this nice, stable, monotonic improvement, right? So you have these tasks that we trained in simulation. You can see they transfer somewhat, but not that well. But in around 15 to 30 minutes of improvement, you can, figure out these contacts and readjust like the tiny bits while your exploration is a lot more directed because you've transferred that from simulation, right? So this is nice because it does a lot better than off-policy methods, which often tend to like tank significantly more, right? So you have methods that like soft actor critic or RLPD that are often unstable, whereas if you have this kind of simple supervised learning procedure, it tends to continue getting better, right? When you look at the learned behavior, you get some interesting things from it. You see that it's often a lot faster. It continues to get faster through the process. And because you kind of have trained in simulation with lots of coverage, you get robustness to a lot of different initial conditions, and that gets better over time, right? And so you can see that you're robust in a lot broader range of positions. And lastly, if you kind of look at the model's performance, you can see that it often corrects for like tiny little mistakes. So for instance, you're initially predicting kind of one of the footsteps wrong, but with a little bit of experience, you figure out how to like predict slip or you try to figure out how to predict contact. And so you just make local adjustments on the dynamics of the model and you don't have to worry about making big policy changes. The other useful thing to analyze here is that if you look at what allows the RL problem to be a short horizon problem, you can see that the value functions are well captured and well transferred from simulation to the real world, even if the policies don't. Right? So you can see that a successful trajectory continues to go up and a failed trajectory has a big drop. Right? And so that's what enables the short horizon RL. Okay, so some insights here is that simulation is wrong, but it can still make real world RL super sample efficient and stable. You can use simulation to reduce the horizon and the action space and make the problem a lot simpler. And if you want to transfer more than just a policy, so you can transfer things like a dynamics model or a value function to make the RL problem a lot easier. Okay, so maybe some last takeaways here are a simulator and a dynamics model are really not that different, right? A simulator maybe extrapolates a bit better. A dynamics model can be easily updated as you get more real data. But both of them have an advantage for RL post training because they give you easy resets, they give you cheap parallelizable samples, and they allow you to reorganize your off policy experience. And the important thing here is that like doing that makes RL kind of shine in that it like um, puts it in a setting where your variance can be reduced. And so overall, I think models are likely to be better than simulators in the long run. But they kind of have the key point is that let's try to put RL in scenarios where it works well. I think there's lots of important problems still. I think Carl is going to talk about some work on pre-training. So I think pre-training for post-training is super important. I think I still think exploration is a hard and underexplored problem. I think we don't know how to explore that well. And I also think that RL, whether it's in the real world or in simulation, is not just an algorithms problem, it's a systems problem. So you have to figure out resets, you have to figure out rewards, you have to figure out all of those things to get it to really scale up. And so I think all of these are exciting things to talk about. Listen to Carl's talk for more on this. And yeah, I think that's it for me.
Thank you. Thank you, Dr. Abhishek Gupta. Yes, so is there anybody to have questions for Abhishek? Hi, Abhishek. I have another question. It's yes. So I find this approach quite promising and inspiring. Simulations are able to capture global progress and value signals for the pre-training of the robotics foundation models. What other roles do you think simulation can play? And additionally, do you believe the simulation is sufficient scalable?
Yeah, good question. So, actually, Carl and I have looked at the role of simulation for things like evaluation, and I think evaluation is a natural use for something like simulation.
Yeah,
Um, beyond evaluation, I think like if you shift the optimization problem one level higher, so if you want to like learn how to explore or learn how to adapt, right? So if you learn like meta level strategies, which are one level higher than just the
yeah,
policies themselves, I think simulation is a great way to do those kinds of things because of all these kind of resetability and extrapolation, all these things that I said earlier, right? So I think getting simulation to do the lowest level control, I think, is bounded by how good your simulation is. But in terms of learning meta level strategies, kind of like environments to practice in, I think it's
yeah,
great for like meta learning and things like that.
yeah. Thank you. Yeah,
Cool.
so is there anybody have any other questions? Yeah, so thank you, Abhishek. Yeah,
Thanks,
thank
all.
you for your wonderful talk. Yeah.